Even after science replaced mythology, the universe still felt understandable. Vast, yes, but structured. Governed by rules we believed we could eventually master, then telescopes improved. And every improvement made reality stranger. First, we learned Earth was not the center of existence. Then we learned the Sun was just one ordinary star among hundreds of billions inside the Milky Way. Then we discovered the Milky Way itself was only one galaxy among countless others, drifting through incomprehensible emptiness. Each discovery shrank humanity further. But even then, there was comfort in the numbers. Scientists believed the universe, while unimaginably large, was ultimately measurable, finite in practice, roughly 14 billion light-years outward in every direction. A cosmic sphere we could slowly map piece by piece. That certainty is now collapsing because the James Webb Space Telescope is revealing something profoundly disturbing. The universe may be far larger, far older in structure, and far stranger than modern cosmology ever expected. And worse, most of it may be permanently unreachable. The unsettling truth begins with something deceptively simple. When you look into space, you are not looking across distance. You are looking backward through time. That idea sounds poetic at first, almost harmless. But once you truly understand what it means, your perception of reality changes forever. Light moves incredibly fast, about 186,000 miles every second, fast enough to circle Earth more than 7 times in a single heartbeat. Nothing in the universe travels faster. That is not merely a technological limitation. It is a fundamental law written into the structure of reality itself. And yet even at that impossible speed, the cosmos is so enormous that light itself becomes slow. The moon we see in the sky is not the moon as it exists now. It is the moon as it was 8 seconds ago. The sun burning above us is not the sun of this present moment. It is an 8-minute-old memory. Every single star visible from Earth tonight is a ghost image from the past. The light entering your eyes left those stars years, decades, centuries, sometimes thousands of years before you were born. Every galaxy is delayed. The deeper we look into the universe, the further backward in history we see. Astronomy is not observation. It is archaeology. The nearest star beyond our Sun, Proxima Centauri, appears as it looked more than 4 years ago. The center of the Milky Way appears as it existed 26,000 years in the past. When our ancestors painted animals on cave walls, the light we now see, leaving that galactic core, was already mid-journey, and distant galaxies. We see them as they existed billions of years before Earth even formed, before oceans appeared, before dinosaurs walked continents, before the sun itself ignited from a collapsing cloud of gas and dust. The night sky is not a live view of reality. It is an archive of dead moments still traveling toward us through darkness. Every photon reaching your eyes tonight began its journey long before human civilization existed. Some began moving before Earth formed. Some originated before our entire solar system coalesced from cosmic debris, and that alone is difficult enough to comprehend. But the James Webb Space Telescope forces us to confront something even more unsettling. The universe does not preserve these ancient messages perfectly, because space itself is expanding. This is one of the hardest concepts for the human brain to intuitively grasp. And the difficulty is not a failure of intelligence. It is a collision between human intuition, which evolved to navigate environments measured in feet and miles, and a reality operating at scales that have no equivalent in ordinary experience. Galaxies are not simply flying away through empty space like debris from an explosion. That image is wrong. Space itself is stretching. Imagine drawing dots on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. Not because the dots are moving on their own, not because they are propelled by any engine or force directed outward, but because the surface itself is expanding beneath them. The distance between dots increases regardless of their individual movement. That is what the universe does. And as space stretches, light traveling through it stretches with it. Its wavelength becomes longer. Bluer light shifts toward red. Red light eventually stretches into infrared wavelengths human eyes cannot detect at all. This effect is called redshift. And redshift is not merely a curiosity. It is one of the most powerful tools in all of cosmology, because redshift acts like a timestamp. The more stretched the light is, the longer it has traveled. The longer it traveled, the further back in time we are seeing. And because the universe has expanded continuously since the Big Bang, more ancient light carries more extreme redshift. Astronomers can look at a galaxy, measure how dramatically its light has shifted toward red, and calculate approximately when in cosmic history that light was emitted. For decades, telescopes like Hubble transformed our understanding of the cosmos. They showed us galaxies in extraordinary detail, nebulae glowing with ionized gas, star nurseries thousands of light years wide, black holes tearing apart companion stars, deep field images showing thousands of distant galaxies packed into tiny patches of darkness, no larger than a grain of sand held at arm's length. At the time, Hubble's discoveries felt almost overwhelming, but Hubble had a fundamental limitation. It primarily observed visible light, the same narrow band of electromagnetic radiation human eyes evolved to detect, and that meant there was a boundary beyond which Hubble struggled to see, not because nothing existed beyond that boundary, not because space ended, but because ancient light had redshifted beyond visible wavelengths entirely. The oldest galaxies in the universe were effectively disappearing from view. Not gone, just hidden. Their light had shifted into infrared. And that is exactly why the James Webb Space Telescope was built. Not simply to see farther, but to see differently. To detect wavelengths of ancient light that had stretched beyond Hubble's reach. Webb is not simply a stronger version of Hubble. It is fundamentally different in almost every meaningful way. Its primary mirror stretches more than 21 feet across, nearly 3 times the diameter of Hubble's mirror, and each of its 18 hexagonal segments is coated with an ultra-thin layer of gold. That detail is not aesthetic. Gold reflects infrared light with extraordinary efficiency. It is the ideal material for a telescope designed to collect photons stretching across billions of light years of expanding space. Unlike Hubble, Webb does not orbit Earth directly. It operates nearly 1 million miles away from us, at a gravitationally stable location astronomers call Lagrange point 2. There, balanced between the gravitational influence of Earth and the Sun, Webb drifts in a slow orbit around an empty point in space while remaining in constant communication with Earth, shielded from heat and sunlight by a giant multi-layer sunshield. Roughly the size of a tennis court, Webb cools itself to temperatures that border on absolute zero. That coldness is not incidental. It is essential because infrared light is associated with heat. Any warmth within the telescope itself would blind its sensors with self-generated radiation. Webb had to become colder than the surrounding space, quieter than the darkness it was built to observe. The telescope had to become cold enough to hear the oldest whispers in the universe. When Webb stares into a region of apparent darkness, it is not seeing emptiness. It is waiting for ancient photons. Photons that have travelled for more than 13 billion years. Photons emitted before Earth existed. Photons stretched almost to invisibility by cosmic expansion. Sometimes Webb collects these photons one at a time over many hours or even days of continuous observation. The telescope holds perfectly still, shielded from interference, gathering faint signals that left their sources during cosmic infancy. And when those images finally emerge, what they reveal is deeply unsettling, because according to long-standing cosmological models, the early universe should have been simple, dim, chaotic. The first galaxies were expected to be small, faint collections of gas, slowly gathering mass over hundreds of millions of years. Gravity, after all, is powerful across cosmic scales, but gravity is also slow. Matter needs time to collapse. Gas needs time to cool and condense. Stars require millions of years to ignite through nuclear fusion, and galaxies require hundreds of millions of years to accumulate enough stars and structure to become recognizable systems. The early universe should have resembled a cosmic construction site, still pouring its foundations. Instead, Webb found skyscrapers, massive. Fully formed galaxies appeared shockingly early in cosmic history. Bright, structured systems emerged only 300 to 400 million years after the Big Bang. To understand how absurdly early that is, consider this analogy. Compress the entire 8 billion year history of the universe into a single calendar year beginning on January 1st. Under that scale, the Big Bang happens at the very first second of January 1st. Earth forms around September. The dinosaurs appear in the final days of December. All of recorded human history occurs in the last few seconds before midnight on December 31st. And these massive, well-developed galaxies, they appear around January 2nd. The universe had barely begun existing, and yet Webb found structures already blazing with enormous quantities of light. Not faint smudges of early star formation, not primitive swirling gas clouds, but bright, large, apparently mature systems exhibiting organized structure. Some contained enormous populations of stars comparable to galaxies. We observe billions of years later. Others showed evidence of complex chemical elements, including carbon and oxygen. That specific detail alarmed cosmologists immediately, because heavy elements do not exist immediately after the Big Bang. The early universe contained almost exclusively hydrogen and helium. These are the simplest elements, formed during the first few minutes of cosmic existence, when temperatures were extreme enough for nuclear fusion, but conditions were far too hot and sparse for complex chemistry. Carbon, oxygen, nitrogen, iron, silicon, the elements that build planets, atmospheres, oceans, and living organisms, these are forged inside stars through nuclear fusion over millions of years. They spread through space only when those stars die, either through stellar winds or explosive supernovae that scatter enriched material across interstellar space. That process takes time. Stars must form, live, die, spread their elements. Those elements must then gather into new gas clouds. New stars form from the enriched material. Some of those stars eventually become massive enough to produce even heavier elements before exploding again. Generation after generation of stellar birth and death builds up the heavy element content of the universe gradually, meaning if Webb observes heavy elements in galaxies only a few 100 million years after the Big Bang, then earlier generations of stars must have already completed their entire life cycles, far sooner than any existing model of physics predicted. The cosmic timeline was collapsing inward. The universe was evolving too fast. Astronomers initially assumed the data had to be wrong. These extraordinary galaxies were nicknamed universe breakers in scientific conversations because their apparent existence seemed to violate established frameworks of cosmic evolution. Scientists recalibrated instruments, rechecked algorithms, searched for observational errors, considered whether gravitational lensing was making distant objects appear brighter and larger than they truly were, questioned whether supermassive black holes at galactic centers were contaminating luminosity measurements, investigated whether dust distributions were distorting calculations. Again and again, the same conclusions returned. The galaxies were real. They were massive, and there were far too many of them. The universe was not slowly learning how to build complex structure after billions of years of preparation. It rushed into extraordinary complexity almost immediately after its birth, and that creates an uncomfortable scientific possibility. No current model fully resolves. What if our understanding of the early universe is fundamentally incomplete? What if the universe itself behaves in ways that modern cosmology still cannot properly describe? Webb did not merely discover a few anomalies that could be explained away. It revealed a persistent pattern. Again and again, across multiple independent observations, astronomers found galaxies forming stars at rates far exceeding expectations. Galaxies becoming massive, far more quickly than standard models allowed. Supermassive black holes growing to enormous sizes when the cosmos was still in its infancy. The deeper Webb looked, the stranger the picture became. And the black holes deserve special attention, because some of the earliest galaxies Webb observed already hosted supermassive black holes, weighing millions or even billions of times more than our Sun. Black holes of that scale in the very young universe represent one of the deepest unresolved problems in modern astrophysics. According to standard models, black holes form when massive stars reach the end of their lives and collapse under their own gravity. These stellar remnants typically begin with masses a few to several times greater than our Sun. From there, they grow by consuming surrounding gas, dust, and stars. They merge with other black holes when galaxies collide and combine. They accumulate mass across billions of years. But growth through these ordinary mechanisms has physical limits. As matter falls toward a black hole and accelerates, it releases enormous energy. This radiation pushes outward against additional infalling material. This natural bottleneck, known as the Eddington limit, restricts how quickly even a hungry black hole can consume surrounding matter. Under the most favorable conditions, building a black hole of 1 billion solar masses through standard accretion processes should require several billion years. The early universe did not offer several billion years, yet Webb keeps finding them. Enormous black holes already fully formed when the universe was still a cosmic infant. Some theorists propose that the very first black holes formed not from stellar collapse, but directly from enormous collapsing gas clouds. Others suggest the first generation of stars were so unimaginably massive, perhaps thousands of times more massive than modern stars, that they collapsed immediately into giant black hole seeds. Some researchers believe black hole mergers in the dense early universe proceeded far more rapidly than standard models predict. Others are exploring whether dark matter itself plays a role in providing faster accretion pathways. None of these explanations fully resolves every aspect of the problem, and that is deeply significant, because the James Webb Space Telescope may not simply be expanding our picture of the cosmos. It may be exposing structural cracks in the foundations of cosmology itself, not cracks that invalidate everything we know, but cracks that suggest our current framework, powerful and accurate as it is within its domain, remains incomplete in ways we are only beginning to appreciate. Then came the galaxy counts, and those numbers changed everything again. For years, the scientific consensus placed the total number of galaxies in the observable universe at several hundred billion, an already incomprehensible figure. This estimate originated primarily from analysis of Hubble deep field observations conducted in the mid-1990s. Astronomers pointed Hubble at tiny black patches of sky that appeared completely empty. After collecting light for days, those patches exploded into images filled with thousands of galaxies at various distances, representing different epochs of cosmic history stacked behind each other in depth. Those images genuinely shocked the scientific community when first released. Then Webb looked into comparable patches of darkness, where Hubble saw emptiness between galaxies. Webb saw more galaxies. faint infrared systems hidden beyond visible wavelengths. Ancient structures Hubble literally could not detect because their light had redshifted beyond its sensitivity range. Entire populations of early galaxies, invisible to previous technology, simply appeared. In one extended survey program, Webb observed a small region of sky for hundreds of accumulated hours of exposure time. The result was staggering, even by the standards of a scientific community already accustomed to extraordinary discoveries. Nearly 800 distinct galaxies appeared inside an area of sky. Most people would glance past without a second thought. 800,000 galaxies in what appeared to be empty darkness, and every one of those galaxies contains stars. Many contain billions of stars. Some contain hundreds of billions. Around vast numbers of those stars orbit planets. Some of those planets orbit within the temperature ranges that allow liquid water. Some may possess atmospheres. Chemistry, the molecular building blocks associated with life as we know it. The scale of what those numbers imply becomes genuinely psychologically destabilizing, if you allow yourself to sit with it long enough. Human civilization exists on one planet orbiting one ordinary star inside one ordinary spiral galaxy, among what may now be estimated as potentially 2 trillion galaxies in the observable universe alone. 2 trillion, and even that enormous number may represent only a fraction of observable reality, to say nothing of whatever lies beyond the cosmic horizon. Because the observable universe itself has a limit, and that limit is where the true existential discomfort begins. Most people, when they first hear that the universe is approximately 13.8 billion years old, assume a straightforward conclusion. If the universe has existed for 8 billion years, and light travels at a fixed speed, then the farthest we should be able to see is 13.8 billion light years in any direction. That reasoning feels correct. It is wrong, and understanding why it is wrong requires grasping one of the most disorienting facts in all of modern physics. While light was traveling toward us across billions of years, space itself continued expanding. The galaxies that emitted the light we now observe were not stationary while their photons made the journey. They were moving away from us the entire time, carried by the expansion of space itself. So although the oldest light detectable by Webb has been traveling for roughly 13.8 billion years, the regions of space that emitted it have moved enormously farther away during that journey. The observable universe is not 13.8 billion light years in radius. It is approximately 46 billion light years in radius, and therefore roughly 93 billion light years across. That number is already so large, it collapses ordinary language. No familiar analogy captures it accurately. The human brain did not evolve mechanisms for intuitively grasping distances measured in billions of light years. We can process the numbers mathematically. We can accept them intellectually, but genuine visceral comprehension remains permanently out of reach. And yet that enormous observable sphere is not the universe. It is only the portion of the universe from which light has had enough time to reach us since the Big Bang. It is the region causally connected to Earth, the region from which information can physically arrive. Beyond the edge of this observable sphere, space continues. More galaxies exist. More stars ignite and die. More black holes collide and merge. More complex chemistry evolves in conditions we will never observe. Entire cosmic histories unfold beyond our reach, not because our telescopes are insufficiently powerful, not because we lack the computational resources to process incoming data, not because some future civilization will not build better instruments, but because space between us and those regions is expanding faster than light can cross it. There are regions of the universe from which light emitted today will never reach Earth. Not in 1,000,000 years, not in 1,000,000,000, not in any amount of time. No matter how vast, the expansion of space outruns even light. And this creates something cosmologists call the cosmic event horizon, a boundary surrounding us in all directions, beyond which causal contact becomes permanently impossible, not temporarily impossible. Not impossible given current technology, permanently impossible given the fundamental physics of an accelerating universe. The James Webb Space Telescope is humanity's most powerful tool for probing the edge of this boundary. When Webb detects a galaxy near the limits of its observational capability, it is seeing an object that was, at the time of light emission, extraordinarily close to the edge of the then observable universe. And the current location of that galaxy may already be beyond the event horizon, already permanently disconnected from Earth in any causal sense. We see its ancient image, but we will never know its current state. It has aged billions of years since emitting the light Webb captures. Stars within it have lived and died. Galactic collisions may have reshaped it entirely. Perhaps it merged with neighboring galaxies to form something unrecognizable. Perhaps a supermassive black hole at its center underwent a period of violent feeding, outshining everything around it. Perhaps its star formation ceased entirely, and it faded into a quiet collection of aging red stars. We will never find out. The universe does not allow that information to reach us. And this is not a temporary limitation. It is a permanent feature of an accelerating cosmos, a feature that grows more severe with every passing year as dark energy pushes more of reality beyond the horizon forever. To truly understand the scale of what Webb is confronting, it helps to trace the history of how humanity's perception of cosmic size has changed over time. For most of human existence, the universe was the sky above the horizon. Stars were lights embedded in a fixed dome of darkness overhead. The sun moved across that dome daily. The moon followed its own rhythm. 5 visible planets wandered against the fixed stars, and beyond the outermost sphere of stars. That question had no scientific answer, because there was no scientific framework to ask it meaningfully. The ancient Greek philosophers were remarkable for even attempting systematic answers. Some proposed the stars were fires burning through holes in a dark celestial sphere. Others suggested they were distant suns. Aristarchus of Samos, working around 270 BCE, proposed a heliocentric solar system. and even attempted to estimate the distance to the Sun using geometric reasoning from lunar observations. His numbers were wrong by a substantial margin, but the method was genuinely brilliant for an era without telescopes or precise measurement tools. For most subsequent centuries, the scale of the universe remained essentially static in human imagination, Earth at the centre. The Sun and planets orbiting nearby, stars embedded in a sphere of indeterminate but not incomprehensible distance beyond. Then Galileo pointed a telescope skyward in 1609, and everything began unravelling. The telescope revealed that the Milky Way, that pale band of diffuse light visible across dark skies, resolved into countless individual stars. The night sky was not a modest collection of a few thousand lights. It contained vastly more, and those stars showed no observable parallax shift as Earth moved around the Sun, suggesting they were extraordinarily far away. By the 1800s, astronomers were beginning to measure stellar distances through parallax observations with increasing precision. The nearest stars were revealed to be light years away, immense distances by any human standard. Yet the Milky Way galaxy was still assumed to contain essentially all of the stars in existence. The universe was the galaxy. Then Edwin Hubble changed everything again. In the 1920s, using the 100-inch telescope at Mount Wilson Observatory, Hubble identified a specific type of pulsating star called a Cepheid variable inside the Andromeda Nebula, a fuzzy patch of light visible to the naked eye under dark skies. Cepheid variables pulse with a period directly related to their intrinsic brightness. By measuring the pulsation period, astronomers could calculate how bright the star truly was. By comparing that intrinsic brightness to how bright it appeared from Earth, they could calculate its distance. The Andromeda Nebula was not inside the Milky Way. It was approximately 2.5 million light-years away, a separate galaxy of its own, containing hundreds of billions of stars, and there were countless others. The universe was not the galaxy. The galaxy was merely one island of stars inside a cosmos containing billions of similar islands spread across unimaginable distances. That discovery alone should have been enough to permanently destabilize human cosmic confidence. But it was only the beginning. Hubble then made another measurement that changed physics forever. He analyzed the light from distant galaxies and discovered something no theoretical framework at the time predicted. The light from virtually every distant galaxy was redshifted, shifted toward longer wavelengths consistent with those galaxies moving away from us, and not merely moving away. The farther a galaxy was, the faster it appeared to be receding. The universe was expanding. Every galaxy moving away from every other galaxy as space itself stretched. Running that expansion backward through time led to a singular moment of extraordinary density and temperature, approximately 13.8 billion years ago. What became known as the Big Bang, not an explosion within space, but an expansion of space itself from an initial state of incomprehensible density. And running it forward led to an equally unsettling conclusion. If the universe was expanding, its future depended on the balance between the energy driving expansion and the gravity pulling matter together. For most of the 20th century, the dominant question in cosmology was which force would ultimately win. Would gravity eventually overcome expansion and pull everything back together in a big crunch? Or would expansion continue forever, gradually slowing but never quite stopping? Then came 1998, and the discovery that changed the future of cosmology permanently. Two independent teams of astronomers studying distant type Ia supernovae as distance markers across the cosmos found results that contradicted every existing prediction. The expansion of the universe was not slowing down, it was accelerating. Galaxies were not simply drifting apart under the momentum of the original Big Bang while gravity gradually restrained them. Something was actively pushing space apart with increasing force, something invisible, something that fills the vacuum of space itself and operates in direct opposition to gravity across large scales, something scientists named dark energy. And that discovery, confirmed repeatedly since, transformed the long-term future of the universe from an open question into something far more disturbing. Dark energy does not merely maintain expansion. It increases the rate of expansion over time, which means the cosmic horizon is not a fixed boundary. It is a closing wall. As expansion accelerates, more and more of the universe passes beyond the point from which light can ever reach us. Galaxies that are currently visible will eventually recede faster than light, their final photons arriving at Earth, and then no more following them. They will vanish from the observable universe forever, not because they are destroyed, but because the universe grows too large for information to cross. The James Webb Space Telescope is therefore operating during a genuinely rare window in cosmic history. A moment when the universe is old enough to have produced complex structures worth observing, but young enough that those structures are still visible. In the far future, an intelligent civilization arising on some planet in the Milky Way would look into the sky and see very little. The great galactic clusters visible today would have long since receded beyond the event horizon. The cosmic microwave background radiation, the afterglow of the Big Bang that still fills the entire observable universe today, would have redshifted into wavelengths utterly undetectable by any instrument. Dark energy would have expanded space to such extremes that only the immediate local group of galaxies, gravitationally bound together closely enough to resist expansion, would remain visible. From that future perspective, the universe would look almost empty. No evidence of cosmic web, no distant galaxies receding in redshift, no cosmic microwave background, no observable trace of the Big Bang itself. A future cosmologist might reasonably conclude that their small cluster of galaxies was the entirety of existence. They would have no way of knowing that trillions of galaxies once lay within observable reach. No way of knowing that a telescope built in the 21st century once captured images of structures formed only 300 million years after the universe began. That knowledge would be gone forever, which means humanity, right now, at this specific moment in cosmic history, occupies a remarkably privileged observational window. We exist late enough that galaxies have had time to form and evolve into complex structures worth studying. And we exist early enough that the evidence of the universe's infancy is still arriving at our instruments. The James Webb Space Telescope is humanity's most sophisticated attempt to use that window before it closes. And what it is finding continues to rewrite everything. To understand the full scale of what Webb is revealing, it is necessary to confront something that most people find deeply uncomfortable. Most of the universe is invisible, not hidden behind dust, not simply too faint for current instruments, not located beyond the horizon, invisible in a more fundamental sense, made of substances that do not interact with light at all. When astronomers map the cosmos and add up everything they can directly observe, including every star, every galaxy, every nebula, every black hole's accretion disk, every cloud of interstellar gas, every dust grain, every particle of visible matter in every form across the entire observable universe, the total comes to roughly 5% of the energy content of the cosmos. 5%. The remaining 95% consists of two substances physicists have named dark matter and dark energy. These names are not descriptions. They are admissions of ignorance. Dark, in this context, means we cannot see it, matter and energy, because these substances affect the universe in ways that resemble how ordinary matter and energy behave, but through mechanisms we do not yet understand. And James Webb is forcing these invisible components into increasingly sharp scientific focus. Dark matter reveals itself through gravity. The first strong evidence for its existence came from galaxies behaving in ways they should not. When astronomers measured how fast stars orbit within spiral galaxies, including our own Milky Way, they found something deeply puzzling. Stars at the outer edges of galaxies orbit far too quickly. If galaxies contained only the visible matter we can detect, the outer stars would not have enough gravitational force holding them in orbit. They should fly off into intergalactic space. The galaxy should be tearing itself apart continuously. But galaxies are stable. They have been stable for billions of years. Something massive and invisible must surround every galaxy, a vast halo of matter extending far beyond the visible disk of stars. Matter that contributes gravitational pull without emitting, absorbing, or reflecting any form of electromagnetic radiation. Dark matter. Further evidence accumulated from observations of galaxy clusters. Clusters contain hundreds or thousands of individual galaxies moving through shared space. If you calculate the total mass needed to gravitationally bind those galaxies together based on their orbital velocities, the result is far larger than the mass of all visible matter combined. Clusters should be flying apart. Instead, they are gravitationally bound systems that have persisted for billions of years. Dark matter holds them together. Then came gravitational lensing. Einstein's general relativity predicts that mass curves space-time, and light traveling through curved space-time follows curved paths. Massive objects therefore act as cosmic lenses, bending and magnifying the light of objects behind them. Astronomers can observe galaxies and clusters and measure exactly how much their gravity bends light from distant background objects. That measurement reveals the total mass present, including invisible components, and consistently, the gravitational lensing requires far more mass than visible matter can account for. Dark matter is real. But what is it? That question remains one of the deepest unsolved problems in all of physics. Dark matter cannot be ordinary atoms in any form. It does not interact with electromagnetic radiation. It passes through ordinary matter almost without effect. It is not antimatter, which would annihilate upon contact with ordinary matter and produce detectable radiation. It is not black holes in sufficient quantities to explain the observations, though black holes may contribute a small fraction. The leading theoretical candidates are hypothetical particles that interact with ordinary matter only through gravity and possibly the weak nuclear force. Particles so elusive that billions of them may pass through your body every second without a single interaction. Enormous detectors buried deep underground search continuously for rare collision events that might finally identify dark matter directly. So far, none have succeeded, and Webb is making the mystery more urgent rather than less. Because when astronomers use Webb to study the earliest galaxies in the universe, they find that visible matter alone cannot explain the structures that formed. Gravity, operating only on hydrogen and helium gas after the Big Bang, would have been too slow, too diffuse, too weak to assemble the massive galaxies. Webb observes in the early cosmos, dark matter had to come first. In the first moments after the Big Bang, dark matter began clumping together under its own gravity. It does not experience radiation pressure the way ordinary matter does. It does not interact with the intense light flooding the early universe. It can begin collapsing gravitationally almost immediately, while ordinary matter is still locked in a hot plasma, unable to condense. Dark matter formed structures first. Invisible gravitational scaffolding assembled itself across the young universe. And then, as the universe cooled and ordinary matter became able to collapse, hydrogen and helium gas fell into those pre-existing dark matter structures. Gas concentrated, dense cores formed. Temperatures rose inside, collapsing clumps until nuclear fusion ignited. The first stars blazed to life inside structures. Dark matter had already built, meaning the visible universe, every star we see, every galaxy we photograph, every nebula we admire in astronomical images, may simply be glowing material draped over an invisible skeleton billions of years in the making. The stars and galaxies are not the primary structure of the universe. They are traces of structure, luminous markers showing us where invisible architecture already existed. And this realization reshapes how we interpret Webb's most disturbing discoveries. When Webb finds massive, fully formed galaxies only a few 100 million years after the Big Bang, the implication may be that dark matter structures, providing the gravitational framework for those galaxies, assembled even earlier. Before any stars existed, before any light was emitted. In total darkness, the universe may have begun organizing itself in ways completely invisible to any telescope. Because no telescope can see dark matter directly, Webb cannot image it. No current instrument can photograph it. We infer it from its gravitational effects, the way you might infer the presence of an invisible hand by observing objects. It moves. And this limitation extends further. Because dark energy, the force accelerating cosmic expansion, is even stranger than dark matter. Dark matter at least behaves like matter in the sense that it clusters gravitationally. It has density. It gathers in clumps and halos and filaments. It participates in the formation of structure. Dark energy does not cluster. It fills space uniformly. Every cubic centimeter of empty space contains the same density of dark energy, regardless of location. Expand a region of space, and the dark energy within it does not dilute. More dark energy appears as more space is created, which means as the universe expands and total volume increases, the total amount of dark energy grows. This is deeply bizarre from the perspective of ordinary physics. Ordinary matter dilutes as space expands. Spread the same amount of mass across a larger volume and density. Drops. The gravitational influence of that matter weakens. But dark energy maintains constant density regardless of volume. It therefore becomes more dominant over time as matter dilutes and dark energy does not. In the early universe, matter and dark energy competed more evenly. Today, dark energy represents approximately 68% of the total energy content of the universe, and its share grows with each passing epoch, which means the future belongs to dark energy. The distant future of the universe is a cosmos dominated almost entirely by an invisible force, driving expansion faster and faster toward a state of maximum isolation. Individual galaxies, or local groups of galaxies, bound tightly enough by gravity to resist expansion, will eventually become lonely islands in a vast and growing emptiness. The space between them will grow and grow without limit, until no light from any external galaxy can ever reach them. James Webb cannot stop that future, but it can give us the clearest possible view of the present. And the present reveals a universe structured by invisible forces in ways that continue to surprise the scientists most deeply familiar with the data. The cosmic web itself is perhaps the most visually striking evidence of dark matter's influence. When astronomers map the distribution of galaxies across the observable universe, the result looks nothing like a random scatter. Galaxies concentrate along enormous filaments stretching hundreds of millions of light years. Filaments intersect at dense nodes where galaxy clusters accumulate. Between the filaments lie vast voids, regions of space spanning hundreds of millions of light years, containing almost nothing. The structure is extraordinary in its organization. It resembles a three-dimensional foam or sponge on incomprehensible scales, or a neural network, or the interior of a living cell. The cosmic web was predicted theoretically before it was directly observed. Computer simulations of dark matter, gravitational dynamics produced structures remarkably similar to what telescopes later revealed. Dark matter filaments formed first. Ordinary matter fell into those filaments, creating the luminous structures we observe. Webb is now mapping the cosmic web at earlier epochs than ever before accessible, seeing its formation when the universe was a fraction of its current age. And even in the early universe, the structural organization is present. The web was not a late development. It began assembling almost immediately, which raises questions about cosmic inflation that become increasingly difficult to dismiss. Inflation refers to a theoretical period in the very first fractions of a second after the Big Bang, during which the universe expanded exponentially fast. Not just fast, incomprehensibly, violently fast. A region smaller than a subatomic particle expanded to macroscopic scales in an interval so brief it has no counterpart in human experience. The theory of inflation was developed in the early 1980s primarily to explain several otherwise puzzling features of the observable universe. Why is the cosmic microwave background radiation so extraordinarily uniform in temperature across the entire sky? Regions of space that should never have been in causal contact with each other, regions separated by distances too great for light to cross in the age of the universe, show identical temperatures to 1 part in 100,000. Without inflation, that uniformity is an extraordinary coincidence. With inflation, it is expected. Before inflation, the entire observable universe occupied a region small enough for thermal equilibrium to occur. Inflation then expanded that tiny equilibrium region to cosmic scales, spreading its uniformity across the entire observable universe. Inflation also explains why the geometry of the universe appears flat, and it explains the origin of the density fluctuations that seeded the cosmic web. Quantum fluctuations on subatomic scales were stretched by inflation to macroscopic sizes, creating slight density variations in the early universe. Dark matter accumulated first in the denser regions. Ordinary matter followed, and over billions of years, the cosmic web emerged from those primordial quantum seeds, the entire large-scale structure of the universe, every galaxy, every cluster. Every filament of the cosmic web may ultimately trace back to quantum uncertainties occurring in the first 10 to the minus 32 seconds of cosmic history. Quantum mechanics and gravity connected across 13.8 billion years of time. And James Webb is now showing us the results of that connection in unprecedented detail. In the scientific community, certain discoveries arrive quietly and accumulate slowly until their weight becomes impossible to ignore. The discoveries Webb is generating are not quiet. They are arriving with the force of accumulated contradictions that no individual explanation can fully resolve. And the scientific conversation around them has shifted substantially since the telescope began returning data. In the first year of Webb operations, several research groups identified galaxies at extreme redshifts corresponding to the first few 100 million years after the Big Bang. These galaxies were larger and more luminous than any theoretical prediction allowed. Initial responses from the broader astronomical community were cautious. Anomalous data is common in astronomy. Instruments require calibration. Algorithms require verification. Extraordinary claims require extraordinary evidence. The verification happened, the evidence accumulated, and the anomalies did not go away. One of the most striking examples involves what are now called massive quiescent galaxies in the early universe. Quiescent galaxies are galaxies that have stopped forming new stars. Their star formation has ceased, leaving them populated primarily by older, redder, dimmer stars gradually dying out. In the modern universe, quiescent galaxies are common. They represent a natural stage of galactic evolution. Galaxies form stars rapidly in their youth, exhaust or expel their gas supplies through various feedback mechanisms, and eventually settle into quiet stellar populations, aging gracefully over billions of years. The problem is that quiescent galaxies require time to reach that state. They must first form, accumulate stellar populations, drive out their gas through supernova explosions or black hole activity, and then coast through their remaining stellar evolution. That process takes billions of years under standard models. Webb is finding massive quiescent galaxies when the universe was less than 2 billion years old. Not only did these galaxies form their entire stellar populations at extraordinary speed, they also shut down star formation completely, in a fraction of the time theory predicts, and nobody fully understands how. Various mechanisms have been proposed. Intense quasar activity, driven by supermassive black holes, might expel gas from galaxies with such violence that no material remains to form new stars. Dense environments in early galaxy clusters might strip gas through ram pressure as galaxies move through hot intracluster medium. Rapid consumption of available gas in extreme star formation episodes might simply exhaust the fuel supply. Each of these mechanisms operates in modern galaxies, but operating them at the required intensity, speed, and scale in the early universe pushes against the boundaries of existing models. And they are not isolated examples. Webb's surveys of early galaxies reveal that the fraction of quiescent galaxies in the early universe is higher than any simulation predicted. The universe was not only building structure too quickly, it was also evolving that structure through its life cycle too quickly, stars forming fast, galaxies maturing fast, star formation shutting down fast, everything moving at a pace that does not fit neatly into existing timelines. The scientific response has been a mixture of excitement and genuine unease. Excitement because anomalies are the fuel of scientific progress. Every major revision of physics began with observations that did not fit existing frameworks. Maxwell's equations conflicted with Newtonian mechanics until Einstein resolved the contradiction with special relativity. The perihelion precession of Mercury did not fit Newtonian gravity until general relativity explained it. The ultraviolet catastrophe of blackbody radiation did not fit classical thermodynamics until quantum mechanics emerged. Webb's anomalies may be pointing toward similarly fundamental revisions, and unease because revising the foundations of cosmology is not a simple or comfortable process, the standard model of cosmology, known as lambda CDM, combining the cosmological constant, representing dark energy with cold dark matter, is one of the most successful scientific frameworks ever constructed. It correctly predicts the cosmic microwave background, radiation with extraordinary precision. It correctly predicts the large-scale structure of the cosmic web. It correctly predicts nucleosynthesis ratios of light elements from the early universe. It successfully describes an enormous range of observations spanning billions of light years and billions of years of cosmic history. But Webb is stressing it in ways that demand attention. And the Hubble tension makes the situation more urgent still. The Hubble tension refers to a persistent, statistically significant disagreement between two independent methods of measuring the current expansion rate of the universe, but expressed as the Hubble constant. One method uses the cosmic microwave background radiation. By analyzing tiny temperature fluctuations in this ancient afterglow of the Big Bang, and feeding that data through the equations of lambda CDM, scientists can predict what the expansion rate of the universe should be today. This method consistently produces a Hubble constant of approximately 67 kilometers per second per megaparsec, meaning for every megaparsec, roughly 26 million light-years of distance. Galaxies recede 67 kilometers per second faster. The other method uses distance ladders built from observable phenomena in the local universe. Cepheid variable stars in nearby galaxies provide distance measurements. Those distances calibrate type Ia supernovae, which then serve as distance markers across much larger scales. This method consistently produces a Hubble constant of approximately 73 kilometers per second per megaparsec. Those two numbers look close, but the discrepancy is roughly 8 to 9%, and at cosmological scales, 8 to 9% is not a rounding error. The statistical significance of the disagreement has grown over years of increasingly precise measurements to a level that makes coincidence or systematic measurement error increasingly implausible explanations. Both methods are well tested. Both produce consistent results when repeated. Yet they disagree. When Webb began operating, astronomers hoped it would resolve the tension by providing more precise Cepheid measurements with greater sensitivity and resolution. Webb did improve the precision of Cepheid measurements substantially. It confirmed that Cepheid-based distances in previous studies were not significantly contaminated by crowding effects that might have biased Hubble Space Telescope results. The tension remained, and in some analyses, Webb made it worse, which means the disagreement is almost certainly not a measurement error. It is a genuine signal. Something real is causing different methods to return different answers. Either one method contains an unknown systematic bias that sophisticated analysis has not yet identified, or the universe genuinely behaves differently than lambda CDM, predicts at different scales or epochs. The second possibility, that our cosmological model is incomplete in some fundamental way, is becoming increasingly difficult to dismiss. Proposed extensions and modifications to lambda CDM are proliferating. Some physicists suggest dark energy is not a true cosmological constant, but a dynamic field that changes over time, sometimes called quintessence. Others propose modifications to general relativity that might explain discrepancies without dark energy. Some suggest additional forms of dark matter with different properties from standard cold dark matter. Others investigate whether early dark energy, an additional energy component, active only in the early universe, might resolve both the Hubble tension and some of Webb's galaxy formation puzzles simultaneously. None of these proposals has yet gained consensus acceptance. None fits all observations simultaneously as well as standard lambda CDM. But they represent the frontier of active cosmological investigation. And Webb is providing data that increasingly constrains which proposals remain viable. The telescope is functioning as a stress test for cosmology. Every image it returns, every spectrum it measures, every redshift it determines, adds another data point to the picture of whether the universe behaves as our equations predict. And increasingly, the answer is mostly, but not completely. The exceptions are few but real. The anomalies are consistent across multiple independent observations. And the scientific community is taking them seriously in a way that would not be possible without Webb's extraordinary capabilities. Just 5. What lies beyond the observable? Universe. There is a question that cosmology has historically treated with caution, bordering on reluctance. What exists beyond the observable universe? For decades, the question was often deflected as unscientific. If something lies beyond the region from which light can reach us, how could any observation ever address it? And if no observation can address it, what distinguishes scientific speculation about it from pure philosophy? That deflection was reasonable as a methodological boundary, but it has become increasingly difficult to maintain, because the physics that describes the observable universe makes specific predictions about what lies beyond it. And those predictions are extraordinary. Begin with the simplest possibility consistent with existing observations, that universe beyond the observable horizon continues much as it does within it. More galaxies, more dark matter, filaments, more cosmic web, more voids and clusters and superclusters. The laws of physics are the same. The density of matter and energy is similar, just more of everything, extending outward for distances that make the observable universe look microscopic. How much more? That depends on the geometry of the universe. If the universe is flat, meaning the geometry of space follows Euclidean rules at the largest scales, then by the simplest inflation models, the total universe is vastly larger than the observable portion. The ratio of total universe to observable universe may be comparable to the ratio of the observable universe to an atomic nucleus. The observable universe would be an almost incomprehensibly tiny bubble inside, an almost incomprehensibly larger whole. If the universe is infinite, the implications become even stranger. In an infinite universe, every possible arrangement of matter and energy must eventually repeat. Not because of any mystical principle, simply because the number of possible configurations of matter in any finite region is finite. Quantum mechanics limits how precisely matter can be arranged. An infinite universe with finite local density contains an infinite number of roughly equivalent regions. And in an infinite collection of finite configuration regions, every possible arrangement must eventually recur, including arrangements identical to the observable universe, including arrangements identical to the Milky Way, including arrangements identical to Earth, including arrangements identical to you. Reading this sentence in this specific moment, somewhere in an infinite universe, if the universe is truly infinite, every possible version of every possible scenario plays out, not metaphorically, not as a thought experiment, as literal physical reality in regions forever beyond our causal contact. This concept, sometimes called the level I multiverse in Cosmologist Max Tegmark's classification system, follows directly from combining inflation theory with an infinite universe without requiring any additional physics beyond what is already accepted. And Webb is not disproving it. Everything Webb observes is consistent with a universe vast enough to render such repetitions physically inevitable. But inflation itself, if taken seriously beyond its most conservative interpretation, leads somewhere even stranger: eternal inflation. In many inflation models, the process of rapid exponential expansion does not simply end cleanly everywhere simultaneously. Instead, inflation ends in some regions while continuing in others. Quantum fluctuations cause the inflation field to behave differently in different locations. In regions where inflation ends, the energy driving it converts into ordinary matter and radiation, producing a hot Big Bang and a universe like ours. In surrounding regions, inflation continues. If those surrounding regions also eventually produce ending zones, each ending zone becomes a separate expanding universe with its own thermal history. And if the inflating regions reproduce faster than they convert to ending zones, inflation continues eternally overall, continuously producing new bubble universes with no end in sight. The result is a multiverse of bubbles. Each bubble is an entire universe, potentially with different physical constants, different particle masses, different fundamental forces, even different numbers of spatial dimensions, depending on how the inflation field settles in each region. Our entire observable universe becomes one bubble among an effectively infinite collection of bubbles, each with its own physical reality, each forever causally disconnected from the others, because the expanding space between them grows faster than light can cross it. This scenario, if correct, renders the question of why the universe has the specific physical constants. It does, partly an observational selection effect. We observe a universe with constants compatible with the formation of galaxies, stars, planets, and intelligent observers, because we are those observers. Other bubbles with different constants may be entirely empty or filled with exotic structures no human physicist would recognize. No current observation can directly confirm or refute eternal inflation. But the theoretical arguments for it are substantial, and nothing Webb has found contradicts it. Meanwhile, string theory and its associated landscape of possible vacuum states provide another theoretical layer, suggesting that the physical laws operative in our bubble universe may represent only one selection from an astronomical number of possible physics, each realized in separate regions of a multiverse that makes the observable universe look microscopic. These ideas exist at the frontier of physics, where mathematics and speculation intertwine, where the boundary between science and philosophy is genuinely contested. Critics argue persuasively that theories making no testable predictions about any observable quantity fall outside the domain of empirical science, regardless of their mathematical elegance. But Webb is pushing toward the edges of observability in ways that keep these questions scientifically relevant, because every measurement Webb makes of the large-scale structure, geometry, and physical constants of the observable universe is a measurement of the bubble we inhabit. And any deviation of those measurements from theoretical predictions might, in principle, be evidence of physics extending beyond our bubble. Evidence of bubble collisions, evidence of variable constants across cosmic scales, evidence that the universe we inhabit is not a complete description of reality. So far, Webb has not found definitive evidence of that kind, but it has found enough anomalies to maintain the possibility as scientifically alive. And that may ultimately be the deepest contribution of the telescope. Not simply revealing the universe as it is, but revealing the limits of our current understanding of what the universe could be. Numbers in cosmology are frequently cited and rarely understood. This is not an intellectual failing of anyone who encounters them. It is a consequence of the enormous mismatch between the scales at which human cognition evolved and the scales at which the universe operates. Human beings evolved to navigate environments measured in meters, to track objects moving at speeds measured in meters per second, to anticipate events occurring over timescales of seconds to decades. Our brains are extraordinarily well calibrated for that domain. They are profoundly poorly calibrated for anything outside it. Consider the speed of light, 0.299,792 kilometers per second, or approximately 186,000 miles per second. This number is cited so frequently in discussions of astronomy that it begins to feel abstract. But consider what it means in practical terms. Light can circle the Earth more than 7 times in a single second. In 1 second, light travels nearly 300 Susan kilometers. The entire circumference of Earth is roughly 40,000 kilometers. In the time it takes to complete a single heartbeat, light travels a distance equal to about 7 trips around the planet. That is fast beyond ordinary comprehension. And yet the universe is so enormous that light becomes slow. Light requires 1.3 seconds to reach the moon, 8 minutes to reach the sun, 2 years to reach Proxima Centauri, the nearest star beyond our sun, 26,000 years to travel from Earth to the center of the Milky Way, 2 5 million years to reach the Andromeda Galaxy, our nearest large galactic neighbour, and 8 billion years to travel from the most distant regions currently accessible to Webb's instruments, 3.8 billion years, the age of the universe itself, travelling continuously at the fastest speed physically possible. And light has still only crossed what amounts to an extraordinarily thin shell of the total cosmos. Now consider the distances in spatial terms. The distance from Earth to the nearest star, Proxima Centauri, is approximately 40 trillion kilometers. Written out, that is 40 million thousand kilometers. A number large enough that it ceases to feel meaningful without a reference point. The diameter of the Milky Way galaxy is approximately 100,000 light years. 1 light year is roughly 9.5 trillion kilometers. Multiply by 100,000. The Milky Way stretches approximately 950 quadrillion kilometers across. A 950 followed by 15 zeros, the distance to the Andromeda Galaxy is approximately 2.5 million light years, roughly 24 quintillion kilometers, and Andromeda is one of the closest galaxies to us. The observable universe, 93 billion light years across, contains distances so much larger that the numbers lose all meaning to ordinary human intuition. What Webb is doing is converting those numbers into images. And images, even images of things far beyond human scale, have psychological weight that numbers alone cannot carry. When Webb releases a deep field image showing nearly 800,000 galaxies in a patch of sky, the apparent size of a grain of sand held at arm's length, the visceral impact of that image carries information that no numerical table can convey. Each of those 800,000 points of light is an entire galaxy. Not a star, not a nebula. A galaxy, a collection of millions to hundreds of billions of individual stars, many surrounded by planetary systems. Some, perhaps many, harbouring conditions capable of supporting chemistry complex enough to produce something capable of looking back. And that tiny patch of Webb imagery represents an almost incomprehensibly small fraction of the total observable sky projected across the entire sky. A full deep field survey would reveal numbers of galaxies that make the word trillion feel inadequate. The revised estimate, informed substantially by Webb's early results, suggests the observable universe may contain upward of 2 trillion galaxies. 2 trillion galaxies. The Milky Way, a relatively large spiral galaxy, contains somewhere between 100 billion and 400 billion individual stars. Multiply those numbers together. The result is the estimated total number of stars in the observable universe, a number so large that if you attempted to count them at 1 per second, and you started at the moment of the Big Bang, you would not finish by today. And all of this, the entire 2 trillion galaxy, hundreds of sextillion star observable universe, may represent only a minuscule fraction of the total cosmos extending beyond the observable horizon forever. The James Webb Space Telescope is not merely showing us more of the universe. It is showing us how much of the universe our previous view had missed. And every expansion of the visible picture implies an even larger expansion of the invisible territory beyond it. This is the true scale revelation Webb is delivering, not simply that the universe is large, not simply that galaxies formed early, not simply that dark matter and dark energy dominate the cosmos, but that the relationship between what humanity can observe and what actually exists may be more radically asymmetric than any previous generation of scientists was fully forced to confront. We are not observers of the universe. We are inhabitants of a tiny, illuminated bubble inside it. And Webb is the most powerful flashlight humanity has ever built, pointed into darkness so vast that even the light from that flashlight can only reach so far. All of this cosmic scale, all of this distance and darkness and invisible structure leads inevitably to one question that human beings find impossible to avoid. Are we alone? The James Webb Space Telescope was not designed primarily as an astrobiology instrument. Its core scientific missions center on galaxy formation, cosmic evolution, and the physics of the early universe. But its capabilities have made it one of the most powerful tools yet available for studying a different frontier entirely: the atmospheres of planets orbiting other stars. Exoplanet atmospheric characterization through Webb represents one of the most scientifically significant developments of the past several years, and one that rarely receives the attention it deserves relative to the telescope's deep field discoveries. The technique is called transmission spectroscopy. When a planet passes in front of its host star from Earth's perspective, a tiny fraction of the star's light filters through the planet's atmosphere before continuing toward us. Different molecules in that atmosphere absorb specific wavelengths of light. By comparing the spectrum of the star during a planetary transit with the spectrum when the planet is not transiting, astronomers can identify which wavelengths were absorbed. And from those absorption patterns, they can identify specific molecules: water, carbon dioxide, methane, oxygen, ozone, the chemical signatures of atmospheres, potentially the chemical signatures of biology. Webb has already produced transmission spectra of exoplanet atmospheres with a precision that was simply impossible with previous instruments. In its first years of operation, Webb detected carbon dioxide in the atmosphere of a hot giant planet orbiting another star. A routine confirmation of expected chemistry in a world far too hot and massive to host life. But proof of capability, the same capability applied to smaller, cooler planets in the habitable zones of their stars. Planets like Earth. The technical challenges are formidable. Earth-sized planets produce much smaller transit signals than giant planets. Their atmospheric absorption features are correspondingly subtle. Detection requires long observation times and extremely precise measurements. The nearest potentially habitable exoplanets require hundreds of hours of Webb observation time to produce usable spectra. But the observations are happening, and the results are beginning to accumulate. The TRAPPIST-1 system has received particular attention. A small, cool red dwarf star lying approximately 39 light-years from Earth hosts 7 known planets, several of which orbit within or near the habitable zone where liquid water could theoretically exist on planetary surfaces. These planets are among the best candidates for atmospheric characterization, with Webb, given their proximity and their star's small size, which makes planetary signals relatively detectable. Webb has now observed multiple TRAPPIST-1 planets. The results have been sobering for those hoping for immediate biosignature detection. At least one of the inner planets appears to lack a substantial atmosphere, consistent with the intense stellar radiation from the active red dwarf, stripping atmospheric gases over time. The habitable zone planets require many more observation hours before confident atmospheric characterizations become possible. But the process is ongoing, and the universe Webb is revealing makes the search for life simultaneously more plausible and more humbling. More plausible because of scale. 2 trillion galaxies, hundreds of sextillions of stars. Even if only a tiny fraction host planets in habitable zones, and only a tiny fraction of those develop life, and only a tiny fraction of those develop intelligence, and only a tiny fraction of intelligent species build technology detectable across interstellar distances. The raw numbers suggest the universe should be filled with life. The equations suggest biology should be common, and more humbling because of distance. Because even if life is common, the universe's scale renders contact between separate civilizations extraordinarily difficult. The nearest stars are years away at the speed of light. Meaningful communication requires years per exchange. Physical travel, even at small fractions of the speed of light, requires centuries or millennia to reach even nearby stellar systems. And beyond our immediate stellar neighborhood, the distances grow to thousands, millions, billions of light years. If a civilization in a galaxy web images from 10 billion light years away began broadcasting radio signals the moment that galaxy emitted the light now reaching Webb's mirrors, those signals would only be 10 billion light years into their journey. They have not arrived. They may never arrive. The expanding universe works against them. The James Webb Space Telescope is showing us a universe populated by trillions of galaxies containing astronomical quantities of potential living worlds, and simultaneously showing us that virtually all of them lie forever beyond reach. The loneliness this implies is of a different character than the ordinary loneliness of biological experience. It is structural loneliness, embedded in the physics of expansion, locked into the geometry of space-time, a loneliness the universe itself enforces. And yet, the same universe that enforces that loneliness also produced the biology that notices it, produced organisms capable of building the James Webb Space Telescope, capable of analyzing spectra from planets 39 light-years away, capable of tracing photons that have been traveling since before Earth existed, capable of asking, in full awareness of the question's weight, whether anything else out there is doing the same. That capability did not have to exist. The laws of physics did not require consciousness. did not guarantee intelligence, did not promise that any part of the universe would ever become aware of itself. And yet, here we are, small beyond cosmological significance, brief beyond geological significance, and somehow asking the largest questions the universe contains. JWST, the physics at the edge of breaking. Every great telescope in history has not only revealed more of the universe, it has eventually revealed the limits of existing physics. Galileo's telescope revealed that celestial objects were not the perfect spheres of Aristotelian philosophy. Newton's mathematical framework for gravity, revolutionary as it was, eventually showed cracks when applied to the precise orbit of Mercury. Hubble's observations revealed cosmic expansion that Einstein's original general relativity equations had not predicted, prompting him to famously call his cosmological constant his greatest blunder before expansion was confirmed to be real and accelerating, making something like that constant necessary after all. Each revolution in observational astronomy accompanied a revolution in physical theory, and Webb may be initiating another one. The anomalies accumulating in Webb's data are not individually conclusive. Any single galaxy forming unexpectedly early could have an explanation within existing frameworks. Any individual measurement tension could reflect systematic errors not yet identified. Science advances through accumulation and verification, not through single dramatic discoveries. But the pattern Webb is establishing is becoming harder to explain away. Too many massive galaxies too early. Too many mature structures in the young universe. Supermassive black holes growing too fast, star formation shutting down too quickly. The Hubble tension persisting and strengthening under Webb's improved measurements. Something is consistently off. And the scientific community is increasingly taking seriously the possibility that the something goes beyond instrumental error or observational bias. One direction under active investigation involves the initial conditions of the universe. Standard inflation models predict a specific statistical pattern for the density fluctuations seeded in the early universe, which later grew into the cosmic web and all the structures within it. That pattern, called a nearly scale invariant power spectrum with Gaussian statistics, matches observations of the cosmic microwave background with extraordinary precision. But does it fully explain the distribution of the largest structures? Observations of very large-scale structure, including enormous galaxy chains and supervoids spanning hundreds of millions to billions of light years, have occasionally produced results that seem statistically unlikely under standard inflation predictions. Some features of the large-scale structure appear to repeat or align in ways that simple inflation would not predict. These potential anomalies in large-scale structure have been debated for years and remain controversial. Webb is now providing data at redshifts high enough to test whether the largest structures in the universe were seeded earlier and grew faster than standard models expect. Another direction involves modifications to general relativity. General relativity is one of the most precisely tested physical theories in history. It correctly predicts the bending of light around massive objects. It correctly describes the inspiral of binary neutron stars. It predicted gravitational waves decades before we built instruments sensitive enough to detect them. It governs the expansion of the universe in ways that match observations across many scales. But some physicists have noted that all precision tests of general relativity occur within our solar system or in closely observed binary systems. At cosmological scales, our only verification of general relativity comes from its cosmological predictions, which we test by comparing observations to the lambda CDM framework. If general relativity behaves differently at the largest scales, the entire framework built upon it would require revision. Some modified gravity theories, including alternatives with names like FA, gravity, or MOND, and its relativistic extensions, propose modifications that become significant at low accelerations or very large scales, while remaining indistinguishable from standard general relativity in regimes that have been precisely tested. Webb's observations of galaxy formation and large-scale structure can potentially constrain these theories, ruling some out and leaving others viable. Additionally, some theorists are reconsidering the nature of dark matter itself. If dark matter is not a simple particle, but something more complex, perhaps self-interacting, perhaps capable of forming compact structures, perhaps transitioning in phase over cosmic time, the details of galaxy formation and evolution might change in ways that could explain some of Webb's anomalies without requiring modifications to gravity or the cosmological constant. The dark matter particle physics landscape remains entirely open. Laboratory experiments have ruled out enormous swaths of candidate parameter space for weakly interacting massive particles. Some theorists are exploring lighter candidates, including axions and sterile neutrinos. Others suggest primordial black holes formed in the early universe might contribute meaningfully to the dark matter budget. Webb cannot directly detect any dark matter particle, but it can constrain the behavior of dark matter through its effects on galaxy formation, providing observational ammunition for theorists working to identify what dark matter actually is. And then there is the question of whether the universe has truly always followed the same physical laws. The fine structure constant, which characterizes the strength of electromagnetic interactions, appears from multiple independent measurements to be identical everywhere in the observable universe to an extraordinary degree of precision. The same is true of other fundamental constants, but should we simply assume this holds everywhere, including regions we cannot observe, including earlier epochs of cosmic history? Some theoretical frameworks allow for slowly varying constants, changing over cosmic time or varying across regions of space. If any fundamental constant differed slightly in the early universe, galaxy formation and evolution might proceed differently than standard models predict. Webb is observing the universe at epochs, when such variations, if they exist, would have been most influential. and it is measuring spectral signatures with enough precision that small variations might eventually become detectable. The frontier is genuinely open. The physics is genuinely uncertain in ways that academic conservatism often understates in public presentations. And Webb is the primary instrument humanity currently has for gathering the data that will eventually distinguish between possibilities. There is a specific kind of vertigo that comes from genuinely confronting what modern cosmology has revealed, not the comfortable wonder of looking at a pretty astronomical image, not the abstract appreciation of large numbers, but the actual psychological impact of sitting with what these discoveries mean for the human situation in the cosmos. It is uncomfortable, and it should be. The history of science has repeatedly required humanity to revise its sense of its own significance. Each revision has been resisted, sometimes violently, and eventually accepted because the evidence demanded it. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of the universe. The universe has no center. Each step moved humanity further from the comfortable position of cosmic significance. But those revisions, enormous as they were, still left something intact. They left the sense that while Earth might not be geographically special, the observable universe was at least the entire arena of physical reality. The everything of existence, even if Earth was not at its center, was still something humanity could in principle eventually map completely. Webb is taking even that away. The observable universe is not the universe. It is a bubble, a causally connected region surrounded by an expanse of reality that may be so much larger as to make the observable portion negligible. And within that observable bubble, humanity's location is not merely geographically mediocre. It is temporally specific. We exist during a particular epoch of cosmic history when the universe happens to be old enough to have produced us, but young enough that the evidence of its origins is still accessible. We exist in what cosmologists increasingly describe as a golden age of observational cosmology, a window in cosmic time when the right combination of factors allows the most complete possible picture of the universe's history. That window is already closing, slowly, by human standards, but irreversibly by cosmic standards. The James Webb Space Telescope is humanity's attempt to look through that window as clearly as possible before expansion dims the view further. And what it finds keeps making the window look smaller. Every new distant galaxy Webb discovers is another reminder that the universe extends far beyond what any telescope can ever reach. Every anomaly in galaxy formation is a reminder that the physical framework humanity uses to understand the cosmos remains incomplete. Every measurement of the Hubble tension is a reminder that something fundamental about the universe's expansion history may still be misunderstood. But there is another way to hold all of this, not as diminishment, as radical context. The universe did not require consciousness to develop. Physics does not demand observers. The laws of nature would operate identically if no eyes ever evolved to notice them, if no brains ever emerged capable of curiosity, if no civilizations ever built instruments to measure light that left galaxies before Earth existed. And yet here we are, not because the universe was built for us, not because consciousness is cosmically inevitable, but because in one small corner of 2 trillion galaxies, on one small planet orbiting one ordinary star, chemistry organized itself into something capable of wondering about all of the rest of it. That may be the strangest thing Webb is confirming. Not the presence of ancient galaxies, not the mystery of dark matter, not the acceleration of expansion, but the fact that a species that evolved to find food and avoid predators on a small rocky world eventually built a machine capable of detecting photons from galaxies that existed before Earth was born, and is now using those photons to confront questions about the nature of reality that the universe never required anyone to ask. The cosmos is not disturbing because it is hostile. It is disturbing because it is indifferent. And yet indifference produced us. 14 billion years of physics, chemistry, and biology, operating without intention or direction, produced beings capable of caring about what the universe is made of. That is not a comfort in the ordinary sense. It does not make the cosmic horizon feel less permanent. It does not make the 2 trillion galaxies feel less overwhelming. It does not resolve the Hubble tension or explain dark energy, but it does mean something that, in a universe of this scale, in a cosmos this old, in a reality this strange, the small patch of organized chemistry reading these words is doing something the universe did not have to allow. Looking back at itself, asking questions it did not have to be capable of asking. Building telescopes it did not have to be able to build. Just 10. The universe we are only beginning to understand. The James Webb Space Telescope has been operational for a handful of years. In cosmic terms, that is not a duration worth mentioning. In the 13.8 billion year history of the universe, the period during which Webb has been gathering data represents a fraction so small it cannot be expressed in any intuitive way. And in those few years, it has already fundamentally changed multiple fields of science. It has pushed back the frontiers of observable cosmic history to within a few 100 million years of the Big Bang. It has revealed massive galaxies and sophisticated structures forming faster than any existing model predicted. It has detected the chemical signatures of exoplanet atmospheres with unprecedented precision. It has strengthened the Hubble tension rather than resolving it, pushing the scientific community toward accepting that something is genuinely missing from our cosmological framework. It has multiplied the estimated number of galaxies in the observable universe. It has confirmed that supermassive black holes existed in the early universe at sizes that current physics struggles to explain. It has begun mapping the cosmic web at the earliest accessible epochs. It has produced images of such extraordinary resolution and depth that professional astronomers describe seeing them as physically affecting. And Webb is expected to continue operating for at least 20 years. The science it will produce over that extended period may be as transformative as its first years have been. Future observations will push further into the earliest accessible epoch of cosmic history. They will accumulate more data on exoplanet atmospheres. They will characterize the cosmic web at higher redshifts with better statistics. They will attempt to resolve or deepen the Hubble tension with improved distance measurements. They will observe more galaxies, more black holes, more stellar populations, more chemical signatures from more cosmic environments, and they will likely produce more anomalies, more patterns that fit poorly into existing frameworks, more questions that force physicists and cosmologists to reconsider assumptions embedded so deeply in current models that most practitioners never consciously examine them. That is how science advances, not through smooth accumulation of confirming data, but through the persistent confrontation of theory with observations that refuse to cooperate. Webb is that confrontation at its most productive, and the universe it is revealing is not the tidy, comprehensible cosmos that mid-20th century cosmology imagined we were converging toward. It is stranger, larger, older in structure than expected, more organized at early times than predicted, dominated by invisible substances whose fundamental nature remains unknown, enclosed in a horizon that expansion continuously tightens, connected at its largest scales by a web whose origins trace to quantum fluctuations in the first microseconds of existence, possibly embedded within a multiverse so vast that the observable universe represents a vanishingly small bubble inside it. And somehow, against all of this, containing beings capable of building instruments sensitive enough to read the ancient light written across all of it. The universe was never what we thought. And every time we look more carefully with better instruments and sharper questions, it becomes something we have to revise our thinking to accommodate. That process is not finished. It may never be finished. But the James Webb Space Telescope has ensured that the next chapter of that revision is the most data-rich, the most precisely observed, and the most rigorously tested in the history of human attempts to understand the cosmos we inhabit. The darkness above us is not empty. It is full of light that has been traveling for billions of years to reach instruments we built in our blink of cosmic existence. And what that light is telling us is this: the universe is larger than we imagined, stranger than we predicted, more organized at its origins than our models allowed, more dominated by invisible substances than any early cosmologists suspected, more temporary in its observable connections than the accelerating expansion will allow future civilizations to appreciate, and more capable of producing conscious observers than a purely indifferent cosmos had any physical obligation to be. The true scale of the universe is not a number. It is not 93 billion light years. It is not 2 trillion galaxies. It is not 13.8 billion years. The true scale of the universe is the distance between what we can observe and what actually exists. A distance that the James Webb Space Telescope is showing us with increasing precision is far greater than we ever imagined, and growing every second, in every direction, without limit without mercy, and without any requirement that we ever fully understand it.